we will move on to the next presenter. And I would ask Dinesh, who's also assistant professor at UC San Diego, in the ECE there at UC San Diego, to come online and get ready to talk about all-weather collaborative perception for autonomous systems.
Can you see my screen?
We can.
Sorry, yeah, keep continuing. Sorry.
No, you're good. Looks like it's coming up. And I know you've had quite a number of honors, named the Forbes 30 Under 30 for the science category worldwide. Also one of the top 35 innovators under 35 in the world by MIT's Technology Review. And we're very interested in the work that you're doing in this space as well. So I'll turn things over to you to take it away.
Thank you for the very generous introduction. Let me get quickly started. I have maybe a lot more slides and I want to keep us on schedule. So let's review perception for autonomous systems. This is one of the biggest reason we have so many accidents, so many self-driving cars killing people around, right? And probably enough to scare you to not go on street itself, right? So one of the biggest problem with this kind of systems is that bad weather, or in general inclement weather, right? I think what is a bad weather? Even a simple fog can make these systems really not work well, right? Just don't see things, right? And start colliding into many other scenarios. So just to summarize, right? How does these things work, right? The way these things work is that they use their camera and lidar, essentially send these waves out and look at the reflections, right? And Trong has shown you these things, right? The problem is that these light-based things have a very small wavelength, and therefore they cannot penetrate through these particles, right? This fog particle or any of these rain particles, right? And essentially create a diffraction pattern. I'll explain you with a scene or scenario, right? So here's what is expected actually of these systems. Okay, they are expected to give you these nice little boxes, and then you can put them on a map, and then essentially you can find your path through it, right? And you essentially can navigate through it, right? So however, if you take a lidar and go into this fog scenario, right, and probably can guess which self-driving car this is, right? But you see that this fog is represented as a box. It thinks there is a object instead of fog, and essentially stops the car, right? And this could be in a whole lot of deadly scenarios. You could imagine something on a highway, a car stopping suddenly in the middle of highway and can collide with a lot of other cars. So in contrast, right, what is wireless signals great is that they can have a much larger wavelength, and therefore they can penetrate through these fog, rain, and other conditions, right? And so the question really we are asking in our research is that can we penetrate through these bad weather, right? Okay. So I think I'm just going to give you a quick sense, right? Radars have been studied for like, I don't know, 100 years now. This is a traditional example of a radar showing how it can do detection of planes and even UAVs, even far, far kilometers away, right? So how has been problem changed, right? Remember, I wanted these 3D bounding boxes, right? So essentially getting a point for each of these cars is not sufficient for me, right? To go and navigate through the scenario. What I really need is I want these really detailed outlines of the cars, and then I can essentially have my car navigate through the entire road scenario. So really the problem has changed significantly, right? It's actually going from detection to imaging, actually. This is what we really need to solve, right? So now we know that its radars are probably good substitute for bad weather, but let's take a look. What's the problem with the radars, right? So this is how your lidar work. You send in a wave, okay? You see whole lot of reflections, and one of those reflections goes back to the lidar, and that gives you the dense points you're seeing on the right side. You can see exactly these nice car structures. I probably think zoom is maybe making it distorted, but still you can hopefully see some cars out there, right? On the other hand, right, if you go to radar, radar doesn't get these reflections back all the time. It always reflects with a specular reflection, right? So only a few reflections goes back to the radar, right? And imagine some edges will come back to you a little bit, right? If the power is enough, right? This leads to a very, very like sparse points, right? I'm just showing you a scene where our car is driving, and you can barely half of the objects are missed here. Okay, I'll show you the performance of these objects, right? Okay. So the first problem is really the reflections not coming back. For example, this is a reflective surface the radar is trying to map. None of these reflections come back, and you don't even see this reflective surface. And imagine this could be a car, right? And you could collide into it right away. So one first challenge is specularity, right? Next challenge is, and just to give you sparsity of the point clouds, right? Since not a whole lot of reflections come back, this car, even with four radars, right, you can barely see that there is a car, right? And I'm just showing a heat map so that it's clearer, right? And this is a wireless inside CAD simulator. We have created this our own simulator, right? And in a way, it really works nicely. But and we have shown it's representative of real world. But any case, the long story short is that the radar point clouds are very sparse. You can barely see anything out of it, right? And finally, right, there is a whole lot of noise, right? Just to show you two overlaid scenes here, we have images, right, and we see points, right, which are nowhere close to associated with this car, right? Similarly, you can see some ghost points here. And these are like a whole lot of issues in terms of multipath interference, right, sensor leakage, and so on and so forth. So really the point is that we have these three problems, right? And I'll tell you our solution in one slide. Our solution is that today's industry standard is to build these 1 degree radars, right? They are spectacularly going to fail to solve these problems. Okay, that's the first message. Our core idea is really to understand these problems, and we understood that there's something very simple needed, right? We came up with an idea of like using multiple radars to essentially overcome all these things. Okay, and we introduce a new point cloud representation to essentially build on top of that, right? So let me just give you one slide introduction of what pointillism is. Pointillism is just a technique where the dots by themselves mean nothing, but when these dots are put together with many other dots, then they start making sense, like in this painting, right? Similarly, right, the radars, the problem is that all these reflections are going away. So even if you took a half degree or even a 0.1 degree radar, right, you would never be able to see this reflective surface. And what if you just put a simple second radar here, right? Okay. And it starts getting reflections back from this surface, right? And it starts mapping this surface, right? Really, that's what our key insight, and it's very simple insight, but it's really powerful, right? And to that extent, right, what we are making, right, point is that we want to place multiple radars at different places, right? Now we essentially go about this and show how you can get optimality and so on and so forth, right? I won't go into this. And we do extensive CAD simulations in wireless insight and get some optimality results as to what distribution is optimal, right? Of placements of multiple radars, right? The point I want to make though here is very simple, right? 1 degree radars are going to fail. The way to go about is that having 5 degree radars, right, which will be same number of antennas but multiple of them placed apart. That's the way to go solve, right? So in a way, you can think of it essentially. It's like these HD cameras which were using multiple frames, stitching them together to create a large, high quality image, right? Similarly, it's the same concept we are trying to apply to the radars, right? Just give you an example, right? Here is a now what you are at, right? You started with a camera image, right? I overlaid some radar points. You see those black dots, and I'm missing this white car. And then with multiple radars, I can start seeing this white car, right? So the point I'm trying to make is that this is our like first observation that by combining multiple radars, I will have all the information which I need. Now, even with this information, right? The problem I have is that I need to still take care of noise. I think I'm out of time. But really, what I'm just saying is that we build a Bayesian network which essentially defines probabilities for each point we are referring, right? And then we essentially do a Bayesian, right? So just let me show you out result here, right? Here's how you see a car, right? With multiple radars, right? The same scene, single radar, this car with multiple radar, a whole lot of more noise, right? And with our algorithm, right? We know the points which have high probability and should be real object versus the points which are blue which are low probability, right? And I can clearly see this are corresponding to this car in a few more images, right? So in summary, right, we got really dense points using radars, right? But we still don't have the boxes, we little boxes we wanted them, right? Okay. And in that end, right, we designed a deep learning network, right? Essentially takes care of, learns the underlying distribution of the radar points and tries to map out the boxes, right? And it's a big network. It's already published. I think it will be presented next week, actually. So you're happy to attend a more detailed talk on this, right? So this was our radar setup, right? Test bed. We have a camera, lidar, and multiple radars, right? Radars are off the shelf, and we have some modifications done as well to these radars to do some enhancements. And we deployed these. We collected. Now it's actually 50,000. I should update these. I have 50,000. We have 50,000 scenes really imaged, and actual scenes, not simulated scenes, right? And we can see a whole lot of these bounding boxes done nicely, right? I'm showing you here a result for a bad weather, right? We were using lidar, radar, and we have a ground truth, and you can see lidar is predicting the depth wrong, right? Okay, the blue dotted line is what you need to match, and radar is predicting this to the dot. Essentially, it's the depth at which this car is, right? Look at this scene, right? I'll show you a video as well. Again, we outperform all the baseline. The first point I want to make is that if you use only 1 degree radar, you'll be somewhere in 30%, right, in detecting actually the images and the things in the highway. And you go shoot down up to 97% with our radars, right? With a little bit more better engineering, you can hit to like 99 or 99.99. I think with our simulations, we see those. And in summary, we also get a whole lot of good 2D bounding boxes, right? And I'm going to show you the video. This is the thing. I think really just to show you again, right? This is like our real data collected, a car moving away, and essentially this bounding box being able to track the fog instead of the actual car, right? This is LiDAR. Our radar points are on top of the car as we showed earlier on. So I think I'll summarize some other work, right? In 2019, we did a whole lot of camera based depth prediction, right? Okay. And now next we did another camera depth prediction, but where we can use synthetic and supervised self-supervised networks, right? And give you a depth prediction even where simulated data can be used to learn about real world, right? And now we are also working towards collaborative camera fusion, right? And essentially the problem here is explained that if there are two cars, right, if you want to combine data from them, right, we are using one object as a common object and essentially learning the relative transformation from one to the other, right? And assuming the sharing, and we can learn these transformation. This black car, vehicle A, can't see right now the vehicle F, the red one, right? With this combining, right, using the tree as a common frame of reference, it can start seeing that there exists a red car on that side. Again, another example, which essentially here A and B, car B cannot see this pedestrian, A can see this pedestrian, and C is seen by both car A and B. It uses C to learn the relative transformation and then predicts where this is, right? And this is under work, right? And it's probably going to submit this CVPR, right? So in summary, I had few additional slides explaining how collaborative things is super important. Given this public forum, I can't present those. I'll quickly get to this chart, right, which essentially shows why you need collaborative perception. It outlines detailed 4 tasks needs to be done, right? And the world of collaborative fusion can solve multi-sensor fusion can solve these problems, right? Mapping, localization, perception, and path planning. We have different problems related to weather, accuracy and range, cost, and urban versus non-urban, right? And I have summarized those. I think this banner is blocking, but the whole point I'm trying to make is that no single sensor can solve this problem. We really need sensor fusion, number one. And number two, we need collaboration. Even with sensor fusion, you will miss out on things, right? So, and towards that, I think all of us, and including are working towards making this feasible. Sorry, I took 13 minutes there. Hopefully, it was still not off time.
Well, thank you so much. Really appreciate it. Fascinating stuff. Always the challenges and barriers of getting that level of accuracy. So I think that's fascinating. I want to note again for those that are attendees, feel free to put any questions that you have in the Q&A. Also, want to note that we have some board members I know that are on as panelists. So you're welcome to unmute and ask questions as we go along. So please feel free to do so with each of the presentations. If you like, just unmute and ask your questions.